So I'd really like to see some work on the next 4 problems. Specifically, I want you to make any negative exponents positive and make any fraction exponents into radicals at a minimum before you write the answer to get full credit. So I took the time in 27 to make the fraction exponent into a radical. The denominator of the fraction exponent becomes the index. The rest of the expression becomes the radicand. And now I'm going to do this properly. I'm going to do the cube root of 8 first and then do the 4th power. So cube root of 8, which I have memorized, but pretend I didn't. And now I'll do 2 to the 4th power. The answer to 27 is 16. I definitely could have just broke out my calculator and entered the problem, and it would have given me 16. I want to see at least this step, because from here I can go to the answer pretty quickly. On problem 28, it has a negative exponent. I want to make the negative exponent positive, then write as a radical, and then reduce. So first, if I have a negative exponent, I can create a fraction with a 1 in the numerator and make that term with a negative exponent have a positive exponent. And then the radical is only going to be in the denominator. It's going to be the same cube root of 8 to the 4th. And that I'm not going to show any more work. I just did that above here. So for a final answer, I'd say that's 1 over 16. And I wouldn't show any work on the 16 because these are exactly the same problems. That probably is not going to happen on the test because on the test I have a test bank, and the test bank for problem 27 is going to be different than the test bank for problem 28. You probably won't get lucky like this. 29 is a fraction exponent to a fraction, which is really unpleasant. But I can still make that into a radical. This is going to be the square root of 16 over 25 cubed. And that cubing is ugly. The numbers would get really big. If I cubed 16 and I cubed 25, I'd get numbers that I don't even care to write. Well, maybe I wouldn't mind writing that. But the numbers get really big. And when I have the opportunity, I'm going to make the numbers smaller rather than make them bigger. I'm going to do the square roots of 16, which is 4, and the square root of 25, which is 5, and then I'm going to cube. I definitely could have done the cubing first and wrote those big numbers down, but if you get to a class where a teacher doesn't let you use calculators, then getting the numbers small is probably better. Again, I could have done this whole problem on my calculator. On the test, to get full credit for a correct answer, I just don't want to see just the answer. I want to see the problem written as a radical, and then at least the first step of reducing. I could go from there to there just fine without my calculator. Problem 30, it has a fraction that has a negative exponent. The instructions for these last 4 problems ask me to make any negative exponent positive first. I make a negative exponent outside a fraction positive by taking the reciprocal of the fraction, and then write it as a radical. I wrote the index of 2 that tells me it's a square root. If I didn't have any index there and just had the radical sign, it'd still be an implied square root. And now I'm going to square root the 25 and get 5, square root the 16 and get 4, and now I'm going to cube the 5 and cube the 4. For an answer, it should be 125 over 64. Next 2 problems are using the rules of exponents with fraction exponents and variables, so they're not particularly nice. My calculator is not going to be very useful. 31, I'm multiplying and the bases are the same. If you're multiplying and the bases are the same, you fix the base. You don't change the base, but you add the exponents. Here the exponents are 7/2 and 5/2. They're fractions with the same denominator. So to add the exponents, I'm just going to add the numerators. and leave the denominator, and then I'm going to reduce the fraction. For 31, my answer is going to be x to the sixths. 32, I'm dividing with like bases. And if you're dividing with like bases, you can subtract the exponents. Unfortunately, these aren't as nice of exponents as I gave you in the problem above, because the exponents don't have their fractions without common denominators. So to get to my answer, I need to make the fractions have the same denominators. So I multiplied the fraction 8 over 3 by 2 over 2 to make it have a denominator of 6. I multiplied the 1/2 by 3 over 3 to give it a denominator of 6. And now I'm just going to subtract the 16 and the 3 and get 13 sixths for my exponent, for my answer. If you wanted to, you could write this as a radical. And then if I wrote it as a radical, then all of a sudden it's a radical that reduces. Oh gosh, I don't expect you to do this. But if you did that, if you wrote it as a radical and reduced the radical, beautiful. But this is what I'm expecting for an answer here. It doesn't say anything about writing the answer with a radical form. So this that I did in my head that might have been too confusing, don't worry about. On 33, I'm going to square the 4, and I'm going to multiply the exponent for the x's. 4 squared is 16. That's not an issue. If I can't multiply 5/2 times 2 quickly, I'll just use my calculator. 5/2 times 2 is just 5. Really, this is 5/2 times 2 over 1, and the 2's cancel into 1's. And the exponent that should be left on the x is just 5. So for 33, it should just be 16x to the 5th for an answer. We get to a couple graphs, and I have a lot of the work done just to save some time. When we did these graphs for square roots, what we started off doing is we took the radicand and we separately set it equal to 16. We took the radicand, set it equal to 9. We took the radicand, set it equal to 4. Took the radicand, set it equal to 1. We took the radicand, set it equal to 0. We took the radicand, set it equal to -1, and we took the radicand and set it equal to -4. And these are going to give me the numbers I put in my x column of my table. So to start off my table, I set the radicand equal to 16. I add 4 to both sides, and that gave me 20 for the first number in my table. The x minus 4, when I set it equal to 9, I'd add 4 to both sides and get 13 for the next number in my x column. The third number in my x column is going to be 8. The fourth is going to be 5. The fifth is going to be 4. And then 3. And then 0. So those are my x's. For each x I need to get a y. Super easy to do. I'll do them on my calculator to be lazy. The first y, I'm going to plug 20 in for the x. I'll do the square root of 20 minus 4. My calculator gives me that 4. And now I'm going to do the square root of 13 minus 4. My calculator gives me a 3. And then the square root of 8 minus 4. My calculator gives me a 2. Square root of 5 minus 4. Calculator gives me a 1. Square root of 4 minus 4. Calculator gives me a 0. And now, depending on what mode I have my calculator in, either my calculator is going to give me something with an I, which is not a real number, it's an imaginary number, or it's going to give me an error. If I'm in mode 1, it's going to give me an error. If I'm in mode 2, it's going to give me an I. Both of these will cause me to put this not real number properly in the right-hand column. So next thing, I do square root of 3 minus 4. And math error, I'm in mode 1, so that's an imaginary or some sort of error message there would be fine. And the last one, when I plug in 0 and do the square root of 0 minus 4, I get another error, clear those out. So these aren't going to be graphed. And I just had my computer graph these 5 points, plotted them there. I even marked those, but it didn't really have to mark those so nicely. So what I needed to do is made a table of values. I did math ahead of time to figure out the x's, used my calculator to get the y's, plotted the points. Now I need to write the domain in the range. And of all these square root graphs that we did, the domain is always going to be some number, comma, infinity for all the square root graphs that we did. Square bracket on the number, round bracket on the infinity. And the range is going to be similar, some number, square bracketed, comma, infinity. And the starting point is going to be the sum number. The starting point of 4, 0, it's at the very left edge of the graph, or it's the start of the domain. So that x coordinate of the starting point is the beginning of my domain because it's the left edge of the graph. Similarly, the y coordinate of that 4, 0 represents the bottom of the graph, so the range is going to start at 0. So this point 4, 0, the x coordinate of it is the start of the domain, the y coordinate of it is the start of the range. This graph doesn't have a right edge. This graph goes forever and to the right. There is no right edge, and when there is no right edge, we say the domain ends at infinity. Similarly, the graph doesn't have a top edge. The graph goes up forever, and when the graph doesn't have a top to it, we end the range at infinity. So that would be as best I can do, as quickly as I can do something decent for 34. 35 is a cube root graph. To get my x's and cube roots, I do this. I do the radicand equals to 64. The radicand equals to 27. These are all perfect cubes. The radicand equals to 8. The radicand equals to 1. The radicand equals to 0. The radicand equals to -1. The radicand equals to -8. The radicand equals to -27. This is probably way too many points. If you just kind of went maybe between x minus 4 equal to 8 and x minus 4 equal to -8, solve those and get a smaller table, it's fine. I just kind of did overkill here. Let me get the numbers for my x column that I used. The first number in my x column is going to be 68. The second number in my x column is going to be 31. Third number in my x column is going to be 12. The fourth number in my x column is going to be 5. And then I'm going to get 4, 3, -4. I'm doing these fast because you can pause the video and get these done better if you need to. But I just took each of the radicands. I took the radicand and I set it next to all the perfect cubes I can start to think of. And realistically, if all you did was these and you skipped this, this, and that, so be it. I don't hardly care. So those are the values for my x's. Now each y, I'll do a few of them on my calculator, but not all of them. The first y, I'll go shift square root to get a cube root. And now I'm going to do 68 minus 4 by changing the x to 68. That gives me my first y of 4. My next one, I'd go shift and cube root 31 minus 4 and give me that 3. And then shift and square root 12 minus 4. And you can get every number in this table. I'm not going to do them all. And then I had my computer program plot all these points. It's probably not that readable, the y values, or any of the values. They're probably not that readable. But nevertheless, that's a reasonable graph. And for the domain and range for all cube roots for us that we're going to graph, every single cube root, They all have the same domain in the same range because they don't have a starting or stopping point. They extend from the far left edge of the x-axis to the far right edge of the x-axis. They extend from the bottom to the top of the y-axis. Every cube root that we graphed in this chapter, the domain and range were double infinities, negative to positive. Now we're going to reduce some radicals. We're getting close to the end of this. I'm going to reduce by making factor trees. So I'm in mode 1 in my calculator. I type the number 40. I hit shift and this quotes our degrees, minutes, second key. Tells me that 40 is 2 cubed times 5. It's a square root. The index is 2. Anytime I get a 2 of a kind, I get one of those in front of the radical. And anything that's not part of a 2 of a kind gets put under the radical and gets multiplied back. The answer to 36 is going to be 2 square root of 10. I'm going to do a prime factor tree for number 37 as I go to reduce the cube root of 108. 108, its prime factoring is 2 times 2 times 3 times 3 times 3. So as a cube root, every time I get a group of 3, I get one of those out in front of my radical. And anything that's not part of a group of 3 gets put under the radical and it gets multiplied back. So in problem 37, I'm going to get a 3 in front of my radical from the group of 3's and 2 2's under my radical, which are going to turn into a 4. So 3 times the cube root of 4 is kind of perfect. A few more reducings. In 38, it's a 4th root, and it has a 5 out front. The 5 that's out front is going to stay out front and get multiplied by anything I might happen to bring out front when I reduce the 240. And I'm going to do my prime factor tree. It's a 4th power, so anytime I get a 4 of a kind, I get one of those out front. Anything that's less than a 4 of a kind is going to go under and get multiplied. So my prime factoring had 4 2's, so I get a 2 out front, and then a 3 and a 5 that weren't a 4 of a kind, they get put under, and they'll get multiplied. For an answer to 38, I'm going to get 10 times the 4th root of 15. 39 wants me to reduce with a variable, the cube root of b to the 5th. It's going to be the same strategy. I'm going to do a prime factor tree, and a prime factor tree for b to the 5th has 5 b's being multiplied. This is a cube root, so anytime I get a group of 3, I get one of those out front, and anything that's not part of a group of 3 gets put back under and it gets multiplied. The b's that I put back under, I'm going to multiply them by adding their exponents, and I'll get a b squared. So my answer to 39 is going to be b times the cube root of b squared. And you definitely can skip some steps and do some work in your head. 40 and 41 are a little more involved. They're like kind of 3 or 4 problems in one. 40 is a square root. I'm going to reduce each piece separately. For the number 150, I'm going to get a 2 and 3 under my radical and a 5 in front of my radical. For the a cubed, I'm going to get an a to the first outside my radical and an a to the first under my radical. The b squared is going to give me a b in front of my radical, but no b under my radical. And the c, because it's not a 2 of a kind, it's going to stay under my radical. So if I try to digest what I have here, I'm going to start off, I'm going to put a 5 outside my radical and a 2 times 3 under my radical for the 150. For the a, I'm going to get an a to the first outside and an a to the first under my radical. For the b squared, I get a b outside the radical, no b under, and the c stays under my radical. So for an answer to 40, it's going to be 5ab times the square root of 6ac. 41's another square root. I need to reduce everything and keep the 3 in my mind. So let me do a prime factoring for 50. 50 equals to 2 times 5 times 5. So I'm going to get a 2 under my radical and a 5 in front of my radical. The x is going to stay under because there's not a pair. And for the y to the 5th, I'm going to get 2 y's in front of my radical and 1 y under. You probably can just write the answer down without showing as much as I'm about to show, but I'll show a little bit of detail here. So the 3 that started in front of my radical is going to stay there. I'm going to bring a 5 out front of my radical from the pair of 5s that came from the 50, and a 2 under the radical from the single 2 from the 50. The x is going to stay under my radical, and for the y's, I get 2 y's outside and 1 y under my radical. Let me just clean this up and get 15 y squared times the square root of 2xy for my answer. You can definitely show less work than that. 42, it's multiplying with i's, and multiplying with i's really isn't any different than multiplying with x's, other than if you get an I squared, you need to replace it with a negative 1. So in 42, to do the multiplication, I multiply 2 times negative 3 and get negative 6. I multiply I times I, add the exponents that are implied of 1 and 1 and get an I squared. And I squared can be replaced with a negative 1. So negative 6i squared is the same as negative 6 times negative 1. And my answer for 42 is going to be positive 6. For 43, the square root of any negative can be turned into a positive if you put an I after the square root. So 5 times the square root of negative 49 is 5 times the square root of positive 49 times I. The square root of positive 49 is 7. So this is 5 times 7 times I. And that's going to give me 35i for an answer. I can't change an I to anything other than the square root of negative 1. It would be odd, but it would be correct to write 35 times the square root of negative 1. That's an alternate correct answer. But you couldn't just write a negative 1. If you wrote a negative 1, it would have to be under a square root sign. (44) has a negative under a square root, which I'm going to make positive by making an I after my square root. 44 has a reducible square root. I'm going to do a prime factoring for 32. And because it's a square root, anytime I get a pair, I get one of those out front. Singles stay under, and the I doesn't get impacted by reducing that square root. So the square root of 32, you get 2 2's out front. I'm going to multiply the 5 that was out front by the 2 2's that I bring out front. Leave the square root of 2 and leave the I. And that's about the best I can do with problem 44. 2 more problems. Each of these problems, I need to get the square root simplified to a single number first. And I'm going to do that on my calculator. So the 45, I need to get 4 squared minus 8 times 7 times 1 down to a single number. I need to multiply the 2 and the 1 in the denominator. And now I'm going to reduce the square root of negative 40. So for the square root of negative 40, I'm going to think of that as the square root of 40 times I, and simplify 40, or the square root of 40, by putting a 2 in front of my radical and a 2 and a 3 under my radical. So the square root of negative 40 is going to reduce to 2 times the square root of 6 times I. So this problem is negative 6 plus 2 times the square root of 6 times I over 2. At some point I need to make this into two fractions. Let me do that now. This is going to be negative 6 over 2 plus 2 square root of 6 times I over 2. And now I'm going to reduce each fraction. The first fraction reduces to negative 3. The second fraction, the 2's cancel, and you just get square root of 6 times I. Let me put my calculator in mode 2 to check this. So on my calculator, if I go mode and 2, I can enter this now. Fraction, negative 6 plus square root 4 squared minus 8 parentheses 7 parentheses 1 over 2 parentheses 1, enter. Yeah, I got issues here. My prime factoring isn't right here. When I did the prime factoring, which I need to be in mode 1 for, I have a mistake. This shouldn't be a 6 under there. Let me do 40 equals shift quotes. This 3 right here should be a 5. So under my radical should be 2 times 5, which should be 10, which makes that should be 10. This should be 10. My answer should be negative 3 plus rad 10 times I. Sorry, I have a key over here that I'm checking, and I was like, oh crud, I didn't match my key. And that's just because I got lazy. I saw this 3 and I don't know. Anyway, so the prime factoring should have been 2 times 2 times 2 times 5, and that made a 10 go under my radical as opposed to a 6. When I had a 3 there, it was all good and well, it was the wrong number. In 46, I'm going to get the underside of the radical down to a single number. The underside of the radical in 46 is negative 4 squared minus 64, which is negative 48. So this problem I can write as negative 10 minus the square root of negative 48, and the 2 times 2 I can write as 4. If I'm in mode 1, I can reduce the square root of 48 and then worry about the I. So for the square root of negative 48, that would be the square root of 48 times I. And 48 is 2 times 2 times 2 times 2 times 3. So I'm going to get, in reducing that, 2 2's in front of my radical and a 3 under my radical. So that square root of negative 48 is 4 square root of 3 times I. So I can rewrite this problem as minus 10 minus, now change this to 4 square root of 3 times I over 4. When I have i's, I need to make the big fraction into two smaller fractions. So my smaller fraction is going to be negative 10 over 4, and then minus 4 square root of 3 times I over 4. This fraction I'm going to reduce by 2. Negative 10 divided by 2 is negative 5. 2 divided by 2 is 2. Part of my answer is going to be negative 5 halves. The other part of my answer, after the minus sign, I'll cancel the 4's and get the square root of 3 times I. So that's 30 minutes, and well, that's as much as I have for you. So let's stop this, and this is everything that's test worthy from the chapter. If you have all this down, you should do well on the test.